Welcome to the Introduction to Electrical Engineering program at Sirindhorn International Institute of Technology, SIIT, Thammasat University. SIIT offers several programs for students to choose. This includes Electrical Engineering Program, EE for short. There are 7 EE faculty members. The chairperson of EE program, Assistant Professor Dr. Phatham Suksompong. His research interest includes wireless communications. Associate Professor Dr. Ballu Sisuchinwong. His research interest includes microelectronics. Associate Professor Dr. Wali Gongpawetnol. Her research interest includes control theory. Associate Professor Dr. Charlie Jalernlab Noppalat. His research interest includes signal processing. Associate Professor Dr. Toichi Kondo from Japan. His research interest includes digital image processing. Assistant Professor Dr. Ittisek Ninkampang. His research interest includes mechatronics. Assistant Professor Dr. Somsak Gittipiyakul. His research interest includes wireless communications. The 2019 EE curriculum is to be certified by the Council of Engineers in Electrical Engineering, Communications, and in Electrical Engineering, Power. The EE curriculum requires 150 credits. It consists of, firstly, general basic courses for 30 credits, including social science, humanities, science and mathematics, and languages. Secondly, major courses for 114 credits. 2.1 Basic courses including basic mathematics and science courses and basic engineering courses. 2.2 Specialized courses. 2.2.1 Compulsory engineering courses offer 2 possible options for students to choose. Option 1 Communication Engineering. Option 2 Power Engineering. 2.2.2 Elective Engineering Courses. Special Studies also offer students 3 possible tracks. Track 1, a senior project track. Track 2, a foreign exchange track. Track 3, an extended training track. And finally, technical elective courses for 6 credits. In this case, the number of students must be more than 15. Option 1, Communication Engineering. There are many courses listed in black and in red. For example, circuit analysis, electromagnetics, signals and systems, electronic circuits, electrical machines, feedback control systems. In particular, courses in red are specifically for communication engineering. For example, digital signal processing, communication networks and transmission lines, data communications and networks, digital communication systems, mobile communications, and broadband communications. Option 2, Power Engineering. Courses are listed in black and in red. Courses in black are exactly the same as those courses in option 1. The only differences, however, are courses in red which are particularly for power engineering. For example, renewable energy, energy conservation and management, electrical power systems, electrical system design, power electronics, and electrical safety. As mentioned earlier, Special Studies offer 3 possible tracks for students to choose. In their last semester, students can choose one of the 3 main tracks. Track 1, Senior Projects for 6 credits, or Track 2, Foreign Exchange Overseas for 6 credits, or Track 3, Extended Training Track for 6 credits. Thirdly, free elective courses for 6 credits. Students may choose any free elective courses not less than 6 credits offered by either SIIT or Thammasat University, including general basic courses. There are many examples of topics which are related to electrical engineering. As an example, this video shows how an electrical signal is generated periodically. Electrical signals are particularly useful for communications engineering and for power engineering. These two videos show how electrical signals can be generated chaotically. The center video shows a top view of a chaotic signal. The right-hand video shows a side view of the same chaotic signal. Although electrical signals can be generated chaotically, they demonstrate a systematic pattern. A transistor is one of the most important microelectronic devices for many applications, including how a transistor can be employed to generate chaotic signals for communication engineering and for power engineering. This video shows how electrical signals can be controlled and displayed. This project was done by Mr. Phatham, Loahavilai, an EE student. Mr. Phatham, Loahavilai, also demonstrated a project how particles of PM1, PM2.5, and PM10 can be measured and recorded over a period of time, and then being transmitted over a channel. Mr. Phatham also took his apprenticeship in summer at CERN, Switzerland. Electrical engineering can be applied to communications. Mobile communications, digital communications, satellite communications, data networks and servers, fiber optics, internet infrastructure, transistor circuits for communications, integrated circuits, very large-scale integration design, industrial robotics, unmanned vehicles, intelligent cars, computer vision, biomedical engineering, transmission lines, high voltage, smart grid technology, renewable energy, possible EE internships. Internships overseas. Further studies of EE graduates are in, for example, America, Europe, and Japan. Possible future careers. More examples of topics related to electrical engineering are also included at the end of this video. Thank you very much indeed for watching.
We use Apache NetBeans for doing the simulation work, and we obtain the most of information and idea by simulation. In this project, we use SolidWorks program to design our model. And we use 3-dimension printer to print this model. To assemble this model, we have 3 main components: Arduino Nano, driver motor, and transducers. The main components of the ultrasonic levitator are the transducers. In this project, we used ultrasonic sensor Mulata, which transforms an electrical input signal to an acoustic wave. The microcontroller based on Arduino Nano is applied to generate the square wave signals, and the motor driver will amplify the signals. Before we start to assemble everything, we need to check the transducer polarity first. When we got all the equipment that we need, we start to assemble everything together accordingly to the schematic that previously shown. This is the model after we assemble everything together. After we simulate, we got this graph. This graph shows force in x-axis and force in y-axis. We use the value that we obtained from simulator and put in the Excel to plot out the graph. We can specify the number of points to be plotted out. In this case, we use 25 points. We use Arduino to control the phase that transducer emit in order to make objects move up and down. From the result that we obtained, we found the particles are float at the nodes of the standing wave, which in this position appear that the wave doesn't move in any direction, and the node said to be the point that has the minimum pressure.
Hello everyone. In this video, we are going to present to you about our senior project. The group members include Pimpisa Kaikun and Shatin Palanskar. The topic is as follows and it emphasizes on speech privacy protection. In semi-open environment, private conversation can potentially be eavesdropped by unintended listeners. Therefore, in this project, we propose a method to provide speech privacy protection by manipulating the conversation in a way that it is unintelligible to the people outside the private conversation zone. The two key parameters that are thoroughly used in this project are STI and RIR. Speech Transmission Index, or STI, is a standardized objective measurement to predict the speech intelligibility. The value of STI ranges between 0 and 1. In this project, STI is limited below 0.3 to ensure the speech privacy. Room impulse response, or RIR, can be considered as a transfer function between the sound source and the receiver. RIR has three main parts, although the late reverberation influences STI the most. Hence, manipulating STI and its late reverberation can affect speech intelligibility. The proposed scheme to protect speech privacy is to construct a manipulated speech by convolution between private conversation and late reverberation. Once the manipulated speech is constructed, it is added to the private conversation so that the speech is unintelligible at the unintended listener's proximity.
This block diagram shows normal conversation, where unintended listeners hear clean speech X convoluted with RIR and added with noise. Previously, open-loop control system is utilized. By adding late reverberation modeled by extended RIR model, speech intelligibility at unintended listener area decreases. We propose method for protecting speech privacy by using differential evolution-based PID control algorithm. The algorithm searches optimal controller gains Kp, Ki, and Kd for each target speech and room. The objective is to minimize steady-state error of the observed speech STI. The blind STI estimator inputs temporal amplitude envelope of the observed signal into convolutional neural network model and output predicted STI. The performance of the system is subjectively and objectively evaluated. For objective evaluation, STIs of the observed speech are recorded and plotted as shown. The result shows that the estimated STI converges to the target STI within 10 iterations for both noiseless speech, the dotted line, and the speech with pink noise, the red line. For subjective evaluation, the subjects were asked to repeat what they heard and rate difficulty and annoyance from 1 to 4. As shown in the table, the word intelligibility rating calculated from ratio of word correctly heard is quite low, and average of difficulty rating is high. Hence, Information of the private speech signals is protected.
We and our entire world are now at the edge of technological advancement. Digital communication is essential, especially to communicate when we need to be separated. Let's know how we can improve digital communications. Meet Bob and Alice. Both Bob and Alice know the following digital representation of their messages. The messages will be transmitted by a communication channel. Bob would like to send a message, I love you to Alice. So he sends 11. But somehow the message got corrupted by noises. Alice got the message 10, goodbye. What Bob now tries to do is to protect the message by hiring B1 and B2. Both B1 and B2 know the codebook. Bob now sends out 11. As B1 receives 11, he knows to encode and send out 101. As the message travels, it reaches B2 as 111. B2 now looks at the most probable input and successfully decodes as 11. Alice finally receives 11, I love you, and they live happily ever after. With this model, we can call B1 and B2 as block code encoder and minimum distance decoder. The problem is, what is the best block code? With close inspection of the encoder, we can see that the encoder maps from k bits input to n bits of encoded message. Although we can search for the best one, but if we try to add 1 or 2 more bits, we will face with enormous space of possibilities. The problem of large search space could be mitigated by implementing techniques that can eliminate redundant cases. The techniques are unique rows, row swapping, column bit flipping, and column swapping. We can also accelerate the search by using several computers to search for the solution. This is called distributed computing. This solution was presented at the ICCIS conference in Wuhan, China. If optimal codes could be easily predicted, we will have a more reliable digital communication with huge gain on efficiency.
Hello, we're from Group BL3. Today we're gonna present about implementation of a simple chaotic circuit through a few programmable analog array. My name is Thanaporn.
My name is Thanaporn.
The final part of our poster is implementation through a FPAA. After we design an FPAA in an analytic design program, we connect to a FPAA board and the result will show in the oscilloscope. For our first result is x in x-axis and x dot in y-axis, and in the left-hand side is the result from digital oscilloscope and the right-hand side is from analog oscilloscope. Second result is x in x-axis and x2 dot in y-axis. Third result is x in x-axis and x3 dot in y-axis. Fourth result is x dot in x-axis and x2 dot in y-axis.